Hello. This is Alexander Bystrov, and today we continue the series of lectures on machine-to-machine technology, Internet of Things. And today our topic is setting up our experiment, the control system of a machine-to-machine network. This will involve the architecture of the network, first of all, and then some ideas about the experiment where we'll control the electrical motor. So the aims of this session is to look at machine-to-machine architectures for the experiments and have a brief overview of the DC motor closed-loop control system, actually the setup of the experiment, and it will be a separate lecture to look at the methods of implementation of those algorithms, partially modeling. In detail, what we are going to look at is connected LANs with routing. So there will be more than one LAN on the laboratory table. Very limited number of Raspberry Pi devices, but pairwise they will be forming small LANs, and then these LANs will be overlapping somehow. This degree of complexity is to allow us experimentation with advanced routing techniques. So we'll be sending packet from one LAN to the other, crossing some uncharted territory of the third LAN. Then we'll have a closed-loop DC control system overview. Interrupts. Well, it will be mostly covered in the next lecture, so it will be mentioned today. The method for measurement of the motor speed, electrical motor speed, well, it's quite simple. There is a special sensor for this, but a sensor generates pulses, not numbers, and these pulses have to be counted, and they'll be counted by means of those interrupts. So there is a method of counting the rotational speed, and then there will be a method of implementing the program. So implementation of the program, it's the next session. Raspberry Pi RS-232 interface, the serial interface will be involved. So Pis have those interfaces, and in order to control the electrical board, the electrical controller for the electrical motor is a PCB board. We need this interface to talk to the board. Why this interface? Because the board is designed in such a way. So the system complicates as we go along. This interface, not just this one, but all interfaces, they will introduce lag or latency in operation of the system, which affects the quality of control. So we will identify those locations where lag appears. It's possible to predict or measure this lag as well, so it's interesting. Communication to the driver board. There's not much to say there. There's just a couple of small formats and the speed of the RS-232 interface, but it needs to be put somewhere in order to have a clear record of this, so we have an idea how we do that. So as a result of today's lecture, we'll have a reasonably good idea what kind of an experiment we are going to conduct. Now, this is the most important picture for the first half of our experiment, which is design of the LAN. So we are constructing, first of all, a number of local area networks, and they are all somehow communicating, and they are constructed out of devices. We are using laboratory devices, which are Raspberry Pis, and there is a central machine for this, whose business is to act as a firewall router. It is an Intel PC. So what we see in this picture, each group of students who are working on this project will be dealing with this architecture, where in red you have devices which do not belong to you, so you cannot modify them, but you can access them somehow. So this is the firewall router, which leads us to the outside world, and through this route we can access, for example, Unix Newcastle ACK, and this is the a machine through which we will be getting access to the whole laboratory setup from home. It is shown in red because it is a pre-configured router and nobody is going to modify its configuration and you don't have accounts on it. So just take it for granted. Now another red device, it's the device which you cannot modify, it's a master PI. It belongs to our setup. It's painted red because we can't modify it, but you will have accounts in it. So from this you will be able to do certain things, and it will be already pre-configured to do some particular routing here. Right. The business of this master PI is to sit on the network and do nothing else but sort of host your local accounts for quick access to the other devices over which you have full control. And also it has a camera, and the camera will be showing the LEDs on the switch, and also, well, LEDs indicate which links, this or that, are active at the moment. So you see the flashing the LED, and you will see how you can make a conclusion which way packets are traveling, whether they are traveling from here to here or from here to there, for example. Right, and the camera will be also overlooking the electrical motor, so when experimenting with this you will see whether it is rotating or not, so it helps. These three machines, they are Raspberry Pis, and I call them Rig Pi. This one, by the way, I call it Master Pi. Why is it a Master Pi? Because it has a special role. It's pre-configured for you, so it gives you access to everything. It has a camera on it, and also it has an interface through which you will be able to reset those machines, those rig machines. And rig machines, it's those which you are experimenting, and they may function, or then you may break them by incorrectly programming, and by resetting you'll be able to return them to the original state and carry on programming. So it's for this. The electrical motor is not shown here, it will be shown later on. It will be connected to these machines. How it will be connected? There will be one connection to the actuator, to the actual motor, right? So it will be done from one machine from here, for example. And another connection will be to the sensor, it will be an encoder, right? For the purposes of design, because we want to eliminate all sorts of complexities when designing. So it will be connected to the same machine at first, but then for the final experiment we will disconnect from here and plug into a different machine, thus introducing communication over the internet. And this communication will be something to blame for excessive latency, and you will see that it will change the characteristics of the motor. So basically it may cause unstable behavior. Right, so in the middle we have the switch. Switch is a silly device. I mean, silly is not clever, not intelligent at all. What it does, it just provides connectivity between all these links. It's a link level device. However, it's not as silly as some sort of a bridge, so it is or a hub. So basically what it does in a smart way, so if communication happens between these two devices, it will somehow keep these two links free from communication, so it will avoid excessive copying the data to the destinations which are not expecting it. So switch usually improves performance of LANs. Now, LANs. All these devices it is potentially possible to connect them to a single LAN. Why? Because they are all connected to somehow bridge, right? And these two interfaces are in fact the same interface, which means that you have 1, 2, 3, 4 connections, and these connections will be actually to this switch. Potentially it's possible to configure everything to sit on the same LAN, and then it will be not very interesting. Why not interesting? Because it will be a trivially simple configuration. What I suggest is to configure the system in such a way it will be one LAN, yellow LAN, called LAN 1. Right? then it will be LAN 2 for these two devices, then it will be LAN 3 for these two devices, then it will be LAN 4 for these two devices. Right? So LANs overlap. How they overlap? So a single device will belong to two LANs. So this one and this one, this one, this one. What does it mean it belongs to two LANs? It means that it has still a single interface, right? But this interface will have two IP addresses. Like for device D, it will have this IP address and this IP address. They call it multi-homing. So one device will pretend that there are two, and it will be possible to set routing in such a way that the packets will be traveling through those virtual devices differently. So when you are trying to send a packet through LAN 1, it will be going this way, and if you're trying to send the packet through LAN 4, it will go this way. It's possible. You'll see how it works. Quite interesting. It's all about programming IP tables inside of those things and routing tables. Normally, you don't do it when you install a computer or a laptop at home. So it's something which is new, and I think it's quite important and interesting. And on top of that, before running the electrical motor, we will experiment with secure shell and set up all sorts of necessary connections here and implement the experiments from the previous lecture on secure shell, and it will be also interesting. Right? Now, what do you see here? So we have those LANs, several LANs. Let's remember the lecture on the internet and our discussion of that. Each LAN is characterized with what? It is an IP address and a net mask. The net mask is those ones in the binary code of the IP address, and the ones are forming continuous range. Not just a range, but continuous field. It starts with the most significant bit, so it starts with this part and goes this way. And how far does it go? You see number 24. And each of these numbers, it is just 1 byte, so it's 8 bits. So it's 8, this is 16, and 24, it's like that. Notation is decimal, so you have to do this kind of mental acrobatics and constantly switch between decimal notations and binary. So the left 3 numbers in the IP address specify a LAN. So within this LAN we can do whatever you want and address devices without a gateway. Right? And if the LAN is not this but this, so number 4 instead of 1, right? So it's a different LAN. So from the device, so from this, for example, device, in order to reach this one, we will have to appoint any devices around us as gateways, and then we will forward the packet, and then it will arrive into this LAN. I decided to give LANs names like LAN 1, 2, 3, and 4, and I gave the network names which start with 192.168. It is a private range, right? And for LAN 1 it will be 1. For LAN 2 it will be 2. For LAN 3 it will be 3. For LAN 4 it will be 4. So it's quite easy to remember. And then I suggest give devices some names, numbers, right? So 1, 2, 3, 4, for example, right? And for example, well, it doesn't really matter how you assign the numbers. Just keep these numbers given in a systematic way, because it will help you thinking. So it's my good advice, but it's not compulsory. There is some node for this device D, you see, so I put here For triple W, what is triple W? World Wide Web, where is it? It's over there. Over there. Yeah. We need to go into this World Wide Web through this router. We don't care how it is configured, we just know that this is a gateway to the large world and has this IP address. So for this triple W, and in this World Wide Web we have Unix Newcastle SUK, for example, that's our communication machine. You can involve it in some sort of experimentation as well, if you wish. It's not strictly necessary for our experiment, but you can. Actually, you can do many more things with this network, right? In the sense that each of those PIs, it also has a Wi-Fi interface, and you can log into the Wi-Fi at the university from the Pi if you configure it, and then you will have many more networks to experiment with, if you wish. Is that you probably don't need it. But for example, if this link fails for some reason, there is a flood, for example, and between the buildings the communication is severed, then you can potentially use Wi-Fi here and connect to the Wi-Fi, and but Wi-Fi is still on the same cable. So. Right. It's just given for an example is given for the sake of an argument, nothing else. So for triple W, for this wide world web, use gateway. Which one? This one. This one. So it's configured. So if you are accessing, for example, Unix Newcastle SUK, then the traffic will go through this guy. If you set up this kind of a rule, where do you set it up? You set it in the routing table. It's advanced router configuration. You'll see how to do it. It's one of the next slides. Well, however, from this device, if you want to reach some other device, for example, device on the LAN 2, this one or that one, they both are on LAN 2, right? Then you will have to use the gateway, which is this device. It's not just this device, but it will use the same multi-homing, right? And the multi-homing implies that you have one address which belongs to one network and the other address which belongs to the other network, right? So here, gateway C, it will be C which is on the network of LAN 4. There will be two addresses here, right? One of them belongs to this network, the other belongs to this network. Why it is important? Because the device D sits on two networks, right? So the device knows everything about hosts which belong to those networks, and it knows how to reach them by using the MAC level, by link level. Right? So it can reach easily the gateway. But if you specify the gateway which is not on these two networks, then it will not be able to fetch the MAC address for this. The MAC address actually is the same for both, for the interface which is on purple and on the blue networks, right? But this will be recorded against the IP address which is on the purple network. But if you try to use the gateway on the blue network, then it will not find the entry in the table. So it is important that gateways belong to the LANs on which the current host sits, one or several LANs. So because the host knows everything in terms of IPs and MAC addresses about the devices which sit on its LANs. Beyond that, has no idea. So for LAN 2, it will need to use this device as a gateway. Is it possible to use some other device? Yes, it is possible. For example, you can program this device and this device somehow to forward the packets there. And if you did that, then you can use this device as a gateway to this part. But this device is not under our control. It will not be programmed to do so. So, bad luck. So I will have to go this way. Does make sense. So everywhere around the switch we will have those IP table, RJ45 cables. The switch has 5 cables connected to this. It will be 1, 2, 3, 4, and 5 is this one. As simple as that. All connections are quite fast. They are either 1 gigabit or 100 megabit, depending upon the version of the Pi which is used. The thing is that we use some Pis which are Raspberry Pi 3B, and some of them which are 3B plus. Those which are 3B, they are 100 megabit interfaces, and B plus, they're faster, there are 1 gigabit interfaces. There's difference between the tenfold difference. It will not show much in our experimentation, first of all. So, but it is in a way important because all the Pi cannot produce packets so that could at very high speed fall directly each other, because the Pi is not that fast. Still, a packet occupies some length of time to transmit. Yeah? So produce the data in the buffer, and then the network card starts sending this packet. So if it is fast internet, 1 gigabit, then it will be a short duration. If it is 100 megabit, it will be 10 times longer duration. So if several sources, several Pis are sending the data through the same network, then there is a danger that we may cause congestion, and it will be the limitation of performance, which is not good. Well, in this area we are not expecting much limitation, because our communication will be quite slow. Here there will be this limit, because this Master Pi will be streaming video, and video is a very intensive process. Megabytes and gigabytes are sent constantly, so this link will be loaded quite a lot. The good news is that the switch can easily alternate between 100 megabit mode and 1 gigabit mode. So if these guys are 100 megabit and this one is 1 gigabit and this one is 1 gigabit, then this link from here to here will be operating fast, and this traffic will not invade the area of these experimental devices. So for us, it should not have a massive impact. Alright, enough looking at that colorful picture, but keep it in mind and keep it handy, it is useful. By the way, that picture is incomplete because you need to fill it in with the actual IP addresses pretty much everywhere. It will be a home task for the next time. That's what I was talking about. For different destination networks, different gateways are used, and this is a part of your coursework to think of that and basically enumerate all combinations from where to where you're sending packets, and make sure that you figured out which device to configure as a router and what commands to issue. And several, in this case 2 LANs, may exist on a single interface. Multi-homing is what I mentioned before. And these are the instructions which you are going to issue. And there is a problem. I apologize for this. Let me fix it. And now the slide is fixed and we can read the command line here. In order to operate a host as a router, so it receives and sends the data. Normally they are not configured to do so, so you need to do certain actions. It was mentioned in a lecture on internet that there are some system level features where you enable forwarding. It's kind of host based, yeah, it's not a firewall just yet, but a place where you can do it quite quickly for the whole host if you want to disable certain features for safety or security. So of course that part needs to be done, and also we need to deal with the firewall. So usually it's a good practice to configure any host to accept no connections whatsoever at the beginning, and then you just open certain particular ports and connections, so it becomes slightly less secure but gains the actual functionality. So first of all, how to open a firewall if it was closed in the first place. In our case, I think it's open by default. Otherwise it will be just a nightmare to start the coursework, right? But make sure that this command has been issued, and the trace of that can be found in the IP tables. For this, in order to see what you have in the IP tables, you type IP tables like this, and there should be an option here -L uppercase for listing, and it will show you the rules which are already there. Okay, anyway, in order to add the new rule, we do IP tables, A to add, forward, it's the chain for forwarding connections, and what are you adding to this? The source from this network, the destination is this network, and the action is accept. If it is reject, then of course nothing will happen, and if it is drop, then this will also be rejected, but rejected in a silent way. So if you just reject, then the packet comes, it's rejected, and generates an error message, travels back, and you can see what happens. So it's a diagnostic message. What kind of protocol for diagnostic messages is used? It's ICMP, Internet Control Message Protocol. So a TCP packet arrives, tries to propagate, but fails, so the response will be in a different format, will be ICMP. However, if this drop, then drives and cannot propagate, but no error generated, just silent, as if there is nothing there, as if it's a disconnected connection. Good for security, to hide your hosts. And if you put accept, then it will be taken by the host, and then it will attempt to do something useful with this packet. So basically here we are permitting forwarding, right? But forwarding may not happen, because you need to explain the host what to do with your packet, and this is how you explain it. So I set up the routing table rules. So there is a table which says that if something arrives from here, then it has to be directed there. Something arrives from here, it has to be directed. So it's a combination of some properties of the traffic to the gateways, or directional way of sending it. Or you can say that wherever it's arriving from, don't care, but if it is aimed at that network, then send it to this gateway. That's exactly what we're going to do. So this command root, it's not just command, it's a program which runs for you, and its business is to communicate to the kernel, to the operating system, what to do with the network, and internally the operating system fills in the table. If you want to look at this table, what's written there, just put root word and nothing else, just root, and just shows the entries there. Right, root, and we're adding an entry to this table, add, and what we say here, network, this one, net mask is this one. Net mask is what? 8 bits, 8 bits, 8 bits, all ones, right? So it's 24 like we used before. And the net is 192.168.2. Right, it's on the left in our picture. And for that network, we need to use the gateway, this one. And this is for the host C, and C sits on this network number 3. Just let's go back, we'll have a look on this. It's the rule for this host, which acts as a router. Not just a router, it's also kind of a normal computer which does all sorts of communication, but also if you send a packet on this, it will attempt to forward somewhere, so it's a router as well. So the rules for this host are such that if it wants to contact hosts which belong to this green network, has no idea about this network because it sits only on the blue and purple. So if it needs to send something over there, then it will use this device as a gateway. So in order to address that second network with this net mask, it needs to use the gateway, this one, which belongs to the network 3. And it can easily send things to the network number 3 because it sits on it. So I'm writing the rules for this guy. Alright, it is just an example. The next to mention is multi-homing. There is by far more about multi-homing. The whole article I wrote it and put on Canvas with detailed explanation. Apparently there are two notations. There's colon notation and dot notation. They have tiny differences, but the differences are not significant for our experimentation. Both of them will work, so both options will work. So it's possible to pretend that a single device is represented as 2 or 3 or many devices, and each device will have their addresses. For this, we need to first of all familiarize ourselves with syntax of how to write scripts for this network interfaces file. Right? It's sufficient to have just an example in front of your eyes and then you get it. Right? Alternatively, read the manual and there will be a full description, which is probably excessive, but you will see that whatever we are doing belongs to this specification, so just make sense of that. It's good to have access to the manuals. And for each interface, it has several lines of text there describing this. So first of all, it says auto, and then the name of the interface, and this is the device, Ethernet 0. Auto means that when you power up the device, the interface comes up and is prepared to work. Allow hot plug, it means that when your Pi or any computer is running, then you can unplug and plug or plug the cable later into the interface and then it will configure itself. So it's prepared to this hot plugging. And then goes the properties of that. So first of all, what kind of interface this? Interface, Ethernet 0, Internet static. So static configuration means that after that there will be several lines which configure it. So you need to specify which IP address it has, which net mask it has, because you need to know the specification to the network. So you don't need to specify the network separately because a combination of its own IP address with a net mask gives you a network, it's computed internally. And then you can specify default gateway. If you don't want, you may not specify default gateway, in which case you will have to go one slide back and do this by hand for all gateways. Right? So if there is just one gateway, you just specify it here. If there are multiple, then you just go to the previous slide and put several lines. Not in this file, but you have to type those commands at the console or place them somewhere else in your system. For example, you can put them into rc.init file. There is such file, we'll discuss this later. The file which is executed when you just start your computer. And then as started, the configuration will be executed and you don't need to type anything, so it's kind of easy. Not fundamental for our course, of course, but just easy. Right, what we are going to do in terms of the experiment. First of all, build our network according to that colorful picture and experiment with this. So we need to verify the correctness of packet routing. So just make sure that each device can send a packet to another device and nothing is lost. How you do it? You ping from one device to the other. right? And then you will be doing a connection with secure shell. So if you can ping, then you will be able to establish a connection with secure shell as well. So how ping works? It sends ICMP packets. It's special packet. Right? So special in the sense that doesn't carry much data. Just arrives to the destination and causes the response. The purpose of that is debugging of networks. And is routed by means of the IP. Right? And IP is sent by means of the link every time. So it means that IP level and link level work. And if they work, then it's quite difficult to make TCP not work. Well, it's possible. This is possible to specify very sophisticated firewalls which will reject TCP networking but pass some particular other IP packets. Yes, it's possible, but normally it's not the case. So it's done, then connect the motor driver board and the sensor. First to the same device, then to two different devices routing through different lines. Right? The same with routing through Unix Newcastle ACK. It's just the only reason of that is to have a slower path. So if you're sending through a building which is through the next kind of door building, then it will be a longer response. And the longer response means that it will impact stability of your motor more. And observe the impact of the connection latency and stability of the closed-loop control system. So far I didn't say anything about secure shell. Well, secure shell requires the experiments as were specified in the previous lecture, and there will be a couple of commands later in the slides about secure shell. I think that the major effort will go into building this network and configuring devices and issuing commands for these devices like this and testing that everything propagates. So internet is quite a complex thing. And with secure shell, just connect between here and here, here and here, and new session started, and just basically 3 commands and that's it. Still description and analysis is necessary. Now, that's the experimental setup. So this is the rig which is connected to the rig Pi, or Pies. It's a diagram. As usual diagrams, we look at them in silent admiration first and trying to identify what we understand here. So what we see here, this block is a DC motor and it's a shaft, and on the shaft we have a brake, also a DC motor. And the shaft continues, and here we have an encoder. Encoder is a sensor. The DC motor is connected to the driver board, and the brake motor is connected to the power supply, and this to also to the power supply, of course, because you need 20 volts, I think, 1 amp, so it's a powerful motor. But the idea is that the whole motor is controlled by this output from Raspberry Pi, which is RS-232 serial interface. There will be a cable coming in, and it controls the motor through the magic of electronics. Right? And there is a special protocol of communication to the board, but it's quite simple. Now the encoder, Well, this thing starts rotating. We don't need to experiment with the brake. The brake is continuously connected. So why need the brake? Because you want to mimic somehow the load on the shaft, because usually there is some load, but if there's no mechanical load, it means that the load will be still present, but it will be dependent on how well the bearings are lubricated. And when the temperature fluctuates, there will be different braking force there, and as a result, in the morning your experiment will be showing different results compared to the afternoon as the room heats up. If you put, if it's not you, it's I. If I put here the brake, that's the DC motor as a brake, an additional small motor, it will load the shaft by far more than normal friction loads, and as a result of this, this load of the break will be dominating, and this additional load due to temperature variation and lubrication of bearings, it will be negligible. So your experiment will become more stable. Easier to make things when they're stable. Right? In the real world, it's the load, right? So then you will have to design a system which controls the motor in such a way it could work under different loads as well. Right? So we are not doing this in our experiment, but potentially it's possible. It's to complicate your life to say that the system should operate under load 1, load 2, and load 3 conditions. I don't do this because there is no way I can run to the lab every time when you need to change the load on the motor. We are doing it remotely. Now the encoder. There will be a separate slide about this, how it works. Basically there is a cable coming out and it is connected to the PI interrupts. And the interrupts will be served by our PI and will create a program, and we launch it as an encoder process. A process is an instance of the executed program. And this process will be looking at the interrupts. So basically when you rotate the encoder, the shaft is rotating, it will be issuing 500 pulses, and 500 again, and 500 again, 500 again. So you need to count those pulses, and if you know how many pulses you observe within a second, then you can draw a conclusion about the rotational speed of the motor. So you need the interval of 1 second, and within the 1 second you count pulses. Each pulse triggers an interrupt, so basically you'll be counting interrupt events there. It's not as difficult as or awkward as in our other module on embedded systems, because here we have a proper operating system in place, so you have a predefined library function which responds to interrupts. How to use this, it's the subject of the next lecture, where we will be discussing algorithms for that. At the moment we need to look at the system itself and get the overall idea about the method. Now the encoder, that's how it works. The encoder sits on the shaft, that's the shaft, it is rotating, right? And the encoder includes a disk, and there are cuts in that, slits cut, right? So the cuts in that, and the cuts are narrow, and the light can go through them, right? On this side we have the source of light, an LED, and light goes through, and on the other side we have a couple of photosensors that are usually photodiodes, and you see they are drawn as if they were kind of slightly offset with regard to each other, and they're really offset, right? Really offset. So each cut during rotation produces a narrow beam of light which grows and goes through, covering one and then the other sensor, right? So it creates one pulse in the other, in one or the other, and their mutual position is such that as this cut moves, it will create this kind of pulse in one LED, in one photodiode, and this kind of pulse in the other photodiode, and you see they're overlapping. So why do we have two of them now? Right? So if the rotation is in this direction, so it's going that way, it means that this LED is first illuminated, this one is second illuminated. So we have this protocol that the first pulse goes up before going down, the second goes up, then the first goes down, then the second one. So the first pulse, the first LED is illuminated first, the second second. Right? However, if you reverse the rotation, it will be the opposite picture. So this one will be first and this one will be second. So if the arrangement between the pulses is like this, then it is rotation clockwise, and if it is like this, then it is anti-clockwise. So two sensors here are used in order to determine the direction. And they're connected to two different inputs into the Raspberry Pi, which interrupts, and you can use them in your programming. The interrupts are signals, as you see, right? And these signals on the board of the Raspberry Pi are represented as a connector. So they're just metallic pins there, and the device are connected to those. And these pins are called general purpose input-outputs of the Pi SoC chip. They are called general purpose rather than interrupt input-outputs because they can serve different purposes, and we can program them to do one function or the other, and you will see how to do that later. Basically, it is just issuing a special command, and then they become receptive to the interrupts. So what is important here is that the encoding of the rotation is done by a disk with cuts, and the optical connection exists. So this is the disk, that's the rotation, that's the axle of that. We have photosensors, and photosensors are duplicated. Why? Because they've got overlapping, in fact. Why? Because then they produce two series of pulses, and if they're offset in phase one way and it's rotating one way, and that's the other way. So that's the whole idea. Altogether are 500 of those cuts. If the shaft rotates one rotation per second, then it will be half a kilohertz frequency of each of these sequences. Many cuts. So it's a very precise kind of positioning system. Now the driver board. So it was the sensor, now the driver board. Without any particular reason, I started with the sensor. We need both of them. The driver board operates on RS-232 interface, and it is a standard interface which also belongs to the general purpose input-outputs of the Raspberry Pi. It is configured in advance, you don't need to do anything about this. It uses duplex mode, some particular speed, which is expressed in bits per second. How you program this speed? For this we need to run a special program, Minicom, who can access those RS-232 interfaces and program accordingly. Because it's important. It's not a very smart interface. It's sending something to the board, and the board is receiving. We need to make sure that we are sending with the same speed as the receiver understands it. So it's not that sort of each pulse is acknowledged. No, there is no sophisticated handshake or negotiation of the speed then. Now, the input format for this interface. We need to produce at the output this kind of format. You remember printf from our C programming, right? That's the format line. So there has to be an integer number, then space, then another integer number, percentage d, it's an integer number. Right? Then \n to separate different words. So this is the input format for the board, because we are talking about the board. Right? For us, this will be the output format. The complicated thing is this one. If you set up, well, the first number, right? The first number is the speed, right? But the speed corresponds to this number. So if it is number 737 is its output, then the shaft is not rotating at all. The board produces no electrical output to the motor. And then, with regard to this 737, we can have increased value, reduced values. If you increase it, then the shaft starts rotating one way, other way starts rotating the other way, clockwise and anti-clockwise. And the range of this change is plus minus 500. Actually, slightly more than 500, but for us it is sufficient to consider 500. So it's left-right direction. The second number, this number, corresponds to enable disable. So it's 1 enable, 0 disable. For us this is quite useless, but we have to use it anyway, so normally it will be fixed to 1. Why would you want to disable it? So If you want to disable, just output 737, it will just stop. In our case, it will be a PID controller which does not need to switch things, it needs to gradually adjust things. So this second number we don't use. Where do we output it? We output it into a device which is represented as a file in our Raspberry Pi, and you just copy the stream there, and the motor will do the appropriate action. For example, you can say echo 800 space 1 and backslash backslash, whatever it means. Backslash backslash means that it will be a backslash symbol produced there. So if you do this without that, then you will see this writing on the screen. Nice standard output. But here we are doing the following: redirecting the standard output into device serial 0. Right? So that's this one. And this device is with wires, it is connected to the board. And then the motor will start rotating. So 800 is slightly more than 737, it will be very slow rotation one way. If you output 900 or 1000, it will be rotating, spinning fast. If it will be 300, so it's below this number, right, it will be rotating the other way around. Well, know that RS-232 has to be enabled in the system settings of the Pi, and I will do it for you in advance. That will be enabled. Just keep in mind, if it doesn't work, then the suspicion is that it was not enabled in the first place. The board, electrical board for which supplies the electrical motor, it takes the power supply, which is plus minus 20 volts. Well, when students work in the lab, it's important to know what kind of voltages there are, because it could be dangerous, and you are not working in the lab, so for you it is safe. Just consider it is connected to the appropriate voltage supply. It will be 20 volts, and the maximum current which it can consume is 1 amp, limited above that. Now interrupts in the controller. And in the interrupts in the Raspberry Pi for the encoder. The system of interrupts in Linux system is standard and quite simple. Basically, you need to output numbers into some special file, and this file is the input of the kernel, which does the magic of reconfiguration for you. The configuration file is here, /c/class/gpio directory, right? And the file there is unexport and export. So the business of unexport is to switch off certain things, and this one creates things, right? So I first show this unexport because when you are doing multiple experiments, you'll just come to use the device first. It's possible somebody else before you left the previous settings, so just remove. So if you output the number into this unexport, it means that the interface for some particular general purpose input-output will just disappear, and when you create it from scratch, it will be reset. Now the same number goes into the export, and as a result of that, a new GPIO is activated, and as it is activated, then in the same folder, that's the folder, right, a new directory appears, and the directory will be this, right? It has to be number 9. Has to be number 9, because we are creating the GPIO number 9, has to be number 9 here. I apologize for this mismatch. Let me make a short pause. I will edit it. I will change it. Right, and now it is fixed, and we are good to go. So I changed 5 to 9, so it's the interface number 9 we are creating, and a new file or new folder is created, and a new directory. Right? If you look inside, there are many files in it, and these are the interface files. For example, you can output the word in into this file, and then it becomes an input channel, right? Then you can say, I'll put the word rising into this file, and then it will start responding to the rising edge. So rising edge of whatever is coming. So it becomes an interrupt. All right. After that, we can access the interrupt input. How? We will be accessing it from our program. So program is written in C, so in our program we will have to include the library poll.h, and we'll be using the function whose name is poll in order to somehow have a response to those interrupts. And this function freezes when you start it, and then sits quiet, and then is released when interrupt appears, right? So basically, if you have a loop, and this loop is poll, then it stops there, and the interrupt arrives, it continues and stops again. So how to count those interrupts? So as released, then just increment the count and it stops again. Okay. So then you can count the number of interrupts, and you need to count them within a fixed period of time. So we'll be using a timer for that. So the idea is quite simple, and it will be discussed next time, and there is a cheat sheet with some pieces of code which is distributed. Please read the manual for this, and there are many words written about that, and they're quite confusing because the manuals are usually written quite badly. Now, sometimes we need to read just one pin. Why do we need to read the one pin? That's because of that. So we are responding to the interrupt on the rising edge, right? So if at this moment this pulse has not started yet, so it's 0, it means that we are rotating one way. If when it happens this pulse is earlier, so it here somewhere, right? Then we will read the value 1, and then we will determine which direction we are rotating. So we need to be able to read a single pin. So we are doing the same business with interrupt number, well, GPIO channel number 10. So first an export in order to reset it, right? Then output number 10 in this export file. As a result of this, we are creating this directory, which is GPIO 10. Inside the directory there will be a file direction, right? We are copying the word in into this one, and then becomes an input channel. Then we are putting the word none into the edge, and now it's not responding to the edge at all, but instead of that we can read from the same directory. Remember this, the same directory, right? The same directory. We can read in the same directory the file whose name is value, and this value contains just a string which is either 0 or 1. You just read it and interpret, and if it is 0 then it is 0 voltage, and if it is 1 then voltage is high. It's 5 volts there, right? How to read it? For example, you need to type cat and then the name of this file, and cat will show you something. This is for shell script, but if you do it from your program, then you need to open this file for reading and get the value from that. So how to open it for reading, an example is given in my cheat sheet, so you will see how to do that. Not quite difficult. Now the details of implementations are following. It will be the next discussion, the next day. Today we need to look at this, how the whole thing should work, the control system. What is a control system, first of all? A control system is kind of a box. On one side you have input, perhaps digital input, could be analog, but in our case it's digital. The other side is some sort of an output, and in this case it is mechanical output, which is rotational speed of the shaft. And the idea of this control system is to make sure that the rotational speed matches the input, and the input is the number. So how it is done? So put the number here. It is somehow converted into this input into the board, and then motor starts rotating, and the rotational speed is measured, and comes back, and the rotational speed is digitized, of course, somewhere here, and is compared to this number which came. Right? So if there is a deviation, then the appropriate action is taken here, and the output to the motor, power output, is adjusted, and as a result it becomes slow or fast, and as a result, basically we are trying to match the measured speed to the demand which comes from here. That's the idea, right? And this is done through this feedback control loop. Subtraction is fundamental to this. This is a so-called PID controller which we have here. What is a PID controller? So the difference between the demand and the measured value, if it is just this value, right? So if there is a small deviation, constant small deviation, then the output will be not much sensitive to this, and you can have a constantly slightly different response from the output object, right? So-called static error. However, if you put an integrator into this block, then a remarkable thing will happen. The remarkable thing is that if you have a very small deviation, a small number, right, and integrate it over time, a small number, small constant, integrate over time will result in constantly increasing this integral, and then over some time it will become noticeable, and the appropriate action will take place here, and as a result we will eliminate the static error, like the system becomes more precise. Right? However, by doing that, we will introduce a lag in the system, some sort of delay. Why delay? Because integrators tend to slow things down. Right? So you know that if you apply sine to the input, the output will be also sine, but shift becomes cosine. And this delay, it's it may impact eventually stability of the system. Why stability may be impacted? Well, let's count the number of integrators here. You know that when you're solving from calculus, you know that when solving differential or integral equation, you're dealing with dynamic system, and if you have a dynamic system of the order 2 and higher, then the solutions are exponents, and they're frequently kind of oscillating, right? If you have an imaginary number in the exponent, then it's oscillating. Let's count the order of the system. So basically, how many integrators are connected to each other in series. So here is the input comes, and here you have some sort of a system. If you apply the input, the output of any regulator will gradually rise, right? But not in 0 times. It may be quite fast, but not in 0 times. Constant input, rising output, looks like it's an integrator. Then if you applied, for example, a quite quick switch from 0 to a constant value to electrical motor, right? So will it start rotating in 0 times? No. It will gradually accelerate. Right? So it's another accelerator, it's another integrator. So the motor has an integrator inside. And any delay in the system, any kind of interval and so on, interface or so on, so there will be somehow related to delay, and there will be adding those hidden degrees of complexity. So the system in general is a complex system in the sense, if you start modeling it very precisely, there will be many integrators, and that becomes a system of very high order. Furthermore, if you remember your dynamic systems and figure out a dynamic model differential equation for a delay element, try doing that. Right? You'll figure out that a perfect delay element or delay line is a dynamic system of an infinitely high order. Nothing is infinite, of course, in this world, because nothing is perfect, but you will get the idea where those complexities are coming from. So there is always a danger that such a motor may start malfunctioning, so basically may start oscillating. The precise discussion about this with mathematical modeling with the tool, instead of MATLAB I'm using Maxima, but it's the same. Well, I will show you the next time I've done this modeling, and I hope it will impress you. So the idea is that all those delays and things they may cause a nasty effect. So in this system there are some integrators. So this controller will include, first of all, proportional control. So whatever changes at the input here should somehow propagate to the output, right? But in order to eliminate static errors, there will be an integrator included here to amplify over time the small difference between the output and the input. So to the proportional integral control. And apparently it makes sense to add here in a clever way some differentiators. Why differentiators? Because integrators here, they are rotating phase of input signals one way. Phase becomes later, right? And differentiators make it earlier. So they will help us to compensate for the problems introduced by the integrators here, and as a result, the system will become faster, basically better. All right. Delay. I told you the delay is a bad thing because it has a very high order models associated with this. So where is the delay? So first of all, when you are applying inputs, then it comes from your Raspberry Pi as a packet RS-232, right? So the decision to send it was done at first. The computer is very fast, but then it takes time to propagate, to actually deliver this packet. And each bit in this packet is sent with a rate of what? 20,000 those per second, so it is a fraction of a second, but still it is a noticeable delay. So this interface will have some latency. Then there will be some latency here to start the program, pass in the program, so it's negligible. Here there will be significant latency because you need to output everything into the RS-232 here. The integrator inside plays its role, and then when measuring the rotational speed there will be a problem. Why? Because you need to count the number of pulses in a unit of time, right? And the unit of time and counting, right? So if this unit of time is long enough, then you'll be producing the data, the result, measurement result, always late by this kind of interval. So there will be a latency there. So there will be latency here, and well, still there will be latency here. It's the pipeline, it's the network, it's the idea of our experiment. It's either in the same host we'll connect it to here, it will be a fast connection, or we will put here a piece of network segment, and then it will be increased latency, and you will see how it impacts the performance of the system. So this pink area, it is the impact of our network to the control system. Yellow area, it's whatever we are designing, and blue area, it's the rig. Right, so what we are designing here is the PID controller and the measurement piece of software who processes the data from encoder, those pulses, measures how many pulses per second. So you will have eventually one program and the other program. They will be run on a single Raspberry Pi without this pink part. You debug it, right? And then you run this in one Pi, this in the other Pi. So this is the rig, and the wire from the sensor will go into the different Pi, right? And this connection eventually will be done through the network, by not just network, but also a secure shell involved. And there will be a delay, significant delay here, and as a result of that, you will see that it impacts the performance. So that's the idea. When you read this picture, you will find this MHZ, right? So M lowercase, not large, not big case. So it means that it's millihertz. Right? The motor is slow. Right? So I suggest to express it in units which are 1,000 times shorter than 1 second, so one rotation per second. Right? So it will be around 1 rotation, 2 rotations, 5, 10 rotations per second, that kind of speed. So it makes sense to measure it in milliseconds. Otherwise, you will have to deal with floating point, and floating point numbers are long. We don't really want to transmit that much. It will introduce more latency in our system. So we'll be trying to use integers everywhere. Now, frequency measurement. It can be done one way or the other. So one way is to have the signal which comes from the sensor, right? And the arrows pointing up, it's when interrupts are striking, right? And this is a set period of time, for example, 20 milliseconds, and 20 milliseconds we count how many times we have incremented the count, and then we reset the count and start counting again. So this is a direct frequency measurement in the sense that we are measuring how many pulses of rotation are in a unit of time. So how accurate do we want to be with this? Should be reasonably accurate. I made an example here. So I just tried to play music with this electrical stuff. So I put a sprocket on the shaft, and it was producing buzzing noise, and different rotational speeds produce different tones, and music becomes unrecognizable if your instrument is very much detuned. So I don't know if there's deviation of 5%, 10%, then it becomes very, very ugly sounds. So you may want to have a reasonably good accuracy. So in order to have reasonably good accuracy, you need to have quite a few pulses measured here. Because it's always plus minus 1 pulse, right? So accuracy is important. So basically, if your this sequence is very slow, so if your rotational speed is very, very low, then you have to either to increase this period, or say that, well, unfortunately my measurement is rubbish, because the number of pulses which I'm counting with this interval is just not enough. So direct frequency measurement is good if this interval is long enough and the number of those pulses are significant. Well, by the way, it's possible to measure not the frequency but the period as well. So it's possible to occupy the period between the two interrupts with multiple measured timing, fixed timing intervals. It is possible, yes. You can do this, but this is adequate for very, very slow rotational speed. So if this gap is very, very long, then it makes sense. Then there will be measurement, direct measurement of the period. So you measure either frequency or period. Frequency is better for fast processes, and period measurement is better for slow processes. Right, direction, right? So this is the first signal, and interrupts are associated with rising H there, right? And we are reading the other signal, right? If it is 0, it means that we are rotating one way. If it is 1, then the other way. Why again? Because it's all about two senses in which way we are rotating. First, second, or second, first. It comes from the mechanical considerations. And finally, the system pipeline. So when we build this kind of measurement device for the speed and the controller, then we need to somehow connect things together. And for the controller, we'll have the process whose name is regulator, or controller, give it any name. For the measurement device, we have this encoder program or sensor. Give it any name, right? So in a simple experiment, we will run one process whose business is to talk to read the interrupts and measure the interrupts within a unit of time. It will produce as a standard output a stream of readable code, which are numbers. Numbers are expressing rotational speed in millihertz, right? So rotational speed of 1 hertz to the number 1000. And then this stream is fed into this program, which is a regulator. So every time it reads something, it performs computations on which correspond to the PID controller and produces the output. Right? So basically what it does, it compares this input with a fixed constant which is set inside, and this constant is defines how fast we want to go, and this input shows how fast we're actually going, and it will compute the difference, and the difference will be put through the algorithm of the PID controller, which is do at the same time integration, differentiation, and addition, multiply all by the coefficients, and put them together as a sum, and then present this sum in an adequate scale to the controller, to the driver board of the electrical motor. So the output of that is human readable. So if you erase this part, then the output will be seen as text, so debugging is easy. And then you just redirect it into the device, and then the device will start controlling the motor. So altogether it's the loop. So this guy sends some data into the serial. Serial interface controls the motor starts rotating, and the sensor starts producing numbers, start pulses. The pulses are coming here, they're counted by the encoder, converted into numbers are coming into the regulator adjusts its output, which goes again into the motor, and it is control loop. Constantly streaming data around. So far so good, it's running in a single Pi, and there is no Internet of Things just yet, right? And here, the next option where we are using actually secure shell and passing the traffic from the sensor to the controller, and the controller, or regulator, right? And the regulator and the sensor, they're on different machines. So in one machine we are running the encoder, and the encoder is reading the data from the sensor, produces a stream of measured data here. The stream goes into the secure shell, into the host, the other host, right? And in the other host we are executing an agent which is the regulator, right? And this regulator will redirect its output into the serial interface in the remote machine. Oof. And then hopefully it will work, or may not work, right? So it depends upon how bad this delay here is. So if the secure shell is extremely slow, then it may actually start malfunctioning. You will see that the system is quite sensitive to the parameters of the coefficients which are in front of those integral, differential and proportional components of the PID controller. Over machine-to-machine network, which connects the FIFO file FF in one host to a similar file in the other host. So this is an example where we don't present. Remember the OSI reference model. So session lab presentation. We don't present here the stream to the other host in a formal way. That is just a single command, right? Here it is an attempt to mimic behavior of a proper machine-to-machine framework for the Internet of Things. So here the encoder reads data from, of course, the sensor and puts it into the FIFO file in one machine. In the other machine, the process CAT reads the data from a pipeline in a different machine and puts it into the regulator and then eventually into the driver board. And between this FF and this FF, we see they are in different hosts. We need to execute this kind of machine-to-machine mapping. Remember we discussed this, how to map a pipeline from one machine to the other. It was now a lecture about secure shell. So these are the experiments which you want to complete, and but these are just the technical setup of those experiments, and I would like you to look and analyze the results. And the results will be all about not just connectivity, logical connectivity, but also about performance and stability. So if the system becomes unstable, it's quite important, isn't it? Again, when constructing your networks, it's kind of not a complete work just yet. So yeah, somewhere at the beginning, somewhere here. It makes sense before running the experiments and the development for the electrical motors, actually to investigate what we've built. So first of all, connectivity, right? Then record, of course, the configuration for all those advanced routers and IP tables and everything, right? Then dump the packets from different interfaces and observe those packets, what they look like. Just produce one or two examples to include in the report and say that, okay, in this block of hexadecimal numbers representing a packet, this is the header, and within this header you have the source and destination addresses. So whatever you can recognize there. So this also ping from one device to the other, measure the time. So the time from here to here will be different from time from here to there because it's a longer path. And if you want to ping from here to Unix Newcastle ACK and return the packet back, it will be even longer because an external network is involved. So I would like to have you to have some kind of sense of the quality and how fast all those things are performance-wise. It's not just about logically connecting different things together. It's also about performance. Right. So, we have covered today what we wanted, and this was the setup for our experiment. But certain details are yet to be discussed, and this is my promise for the next time. And the next time we will look at, first of all, structure of our programs. Right, and there is a cheat sheet. I need to familiarize you with that. And at the model of the electrical motor and the whole control system, because we need to have the most basic background on PID controllers first. Right, I know that many of you are not engineers in automation and control, and these days somehow they isolate computer engineers and electronics engineers from control theory for a reason unknown to me. Usually in the past it was the same science. Right, so with this I complete this talk, and I will see you the next time. Goodbye.